and welcome to this video, revision video on AQA alkenes. My name is Chris Harris. I'm from AlleryTutors.com, and basically we're just going to go through the alkenes topic and give you a quick overview of this topic to make sure that you're obviously getting the right information and to make sure that you've covered everything that is on the specification in the alkenes topic, like I say. These PowerPoints that I'm using on here, they are available to be purchased. If you just click on the link below the video in the descriptions box, and you'll be able to get them there. You can use them for revision, do whatever you want with them really, but they're quite a handy addition to your other revision material that you may have as well. Okay, so like I say, this is linked to the specification. These are the specification points for AQA. Okay, right, so let's have a look first. So we're looking at the introduction to alkenes. So basically these are unsaturated hydrocarbons. So this means that they obviously contain double bonds, and they have the general formula CnH2n. And now this general formula obviously only applies if you've got one double bond in the molecule, and this is what we're assuming with all of these alkenes in this topic. Okay, so they are hydrocarbons, just like alkanes. They contain hydrogen and carbon only. They're unsaturated. They have one double covalent bond, and they undergo addition reactions, which you'll see later on. So here's some examples. This is ethene on the left there, which is CH2CH2. This is the structural formula for it. This is the displayed formula. And this one, which is buta-1,3-diene, this one's got two alkenes, two double bonds. So again, here's the structural formula for it. Make sure you can identify the alkene as a displayed and structural as well. Okay, and the double bonds, they have a high electron density, loads of electrons here. This makes them pretty reactive. You also get cycloalkenes as well, and these have two fewer hydrogens than their straight chain counterparts. So obviously these have, well, the main reason is because the whole thing loops back on itself, and obviously we're using up space where there would have been hydrogens in a straight chain to join onto another carbon. So this is cyclopentene C5H8, so just watch out for them as well. Okay, so like I say, these things undergo addition reactions, and alkenes are attacked by electrophiles because they have double bonds. Okay, so the double bond, like we said, has loads and loads of electrons. It's attacked by electrophiles, and basically the electrophile adds to the molecule. This is why we call it addition reactions. Okay, so the electrophile is an electron pair acceptor. So remember, we looked at nucleophiles as well. You need to know about them. And nucleophiles have them lone pair of electrons. Well, these are just kind of like the opposite. So these accept the electron pair, and basically they're deficient in electrons themselves, and they are attracted to that double bond. So examples of electrophiles are things with a positive charge like NO2+, H+, etc. So these have a deficiency in electrons. Or you can use polar molecules with a delta positive, so things like HBr, H2SO4, etc. And we're going to look at them examples very soon. So all electrophilic addition reactions, we use the curly arrow, obviously to show mechanisms. It always starts from the double bond. Very tempting to draw it the other way around, but it must start from the double bond because that's where the electrons are. And the curly arrows always show where the electrons are going from and where they're going to. Now, most of the electrons are obviously in the double bond, so this is obviously a type of addition reaction. This is the electrophile, the E+, just put the letter E to symbolize an electrophile. However, the electrophiles could be delta positive as well, as I said before. Okay, and basically this is accepting electrons from the double bond, and we're adding onto it. So you'll see this a lot. Okay, so let's look at the first mechanism, because there's quite a few in this one. And we're going to add bromine to it. And basically this is a test for an alkene. So if we add bromine water to an alkene, it should decolorize. And this is basically a sign of an alkene. So adding bromine water to an alkene, it causes a color change from browny orange, because that's the color of bromine, to colorless. Because the product that we produce is colorless. It doesn't actually have a color. So that's why it's decolorizes it. basically your bromine is the electrophile, and this adds to the alkene, and it forms a dibromoalkane. And like I say, this is colourless. So let's have a look at the mechanism here. So you can see here that the Br2, this is a little bit tricky, the Br2 normally isn't polarized because they're both as electronegative as each other. However, when the bromine molecule approaches an area where there's loads of electrons, like a double bond, the electrons shift to the opposite side of the molecule because they're repelling each other. And just temporarily, when this is near the alkene, we get this dipole that's being created. You can see here that the bromine on this side has got a delta positive because it's closest to the double bond. So the electrons that were here are now being shoved over to the left-hand side of the molecule. So that's quite important. So we do create this kind of induced dipole. And we have obviously this electron pair is in the double bond. We've got loads of them there. This is attracted to the delta positive. And what we then do is then break the bromine bond. So let's have a look at the arrows. So curly arrow going from the double bond to the bromine with the delta positive on. And then because obviously this is forming a bond with the bromine, this bond has to break. So the electrons in that single bond go into the bromine, which you can see on there. Okay, so what we form is a carbocation intermediate. Okay, intermediates are basically just molecules which are formed in the middle of a full reaction, and this is an example of one. We call it carbocation because we've got a carbon with a positive charge. Cations are positive, carbo for carbon. So it's a carbocation, and what we have, there's the bromine, look, that we've added on. Notice the double bond's now gone because we've broken it, but we have this single bond remaining, and the bromine is now attached onto the side there. We then have, obviously, our Br minus that was left over with a lone pair, and obviously this is going to go and attack the the positive carbocation like this, and obviously then you're going to form your colourless 1,2-dibromoethane that's made. And you can see what we've done. We start with an alkene and we produce our colourless dibromoethane molecule. It can be another alkene. It doesn't have to be ethane, but ethene. But there's your product there. So it's colourless. Okay, let's look at a slightly easier example. Very similar mechanism. In fact, the mechanism is the same. So alkenes react with hydrogen halides to form halogenoalkanes. Okay, so let's have a look. So we're going to use HBr as an example, but you could use other halogens as well. But HBr follows the same mechanism as the addition of a halogen, like we've seen before, and it can apply to other halogen halides, like I say. So here it is here. Now the difference with this one is that it's polarized. So there's no temporary dipole being created as a permanent dipole. You can see you've got delta positive, delta negative. And obviously we've got the electron pair in here in the double bond, and that's going to go in and attack that delta positive hydrogen, which is then going to break the bromine. You can see it's just the same mechanism as before, okay, just using a different molecule. Now, obviously what we're doing here now is we're adding our hydrogen. There's the hydrogen that we've just added on. There it is. Double bond's broken, again carbocation formed, and there's our bromide ion that's left behind, which is there, and then this is basically going to go in and attack that that positive carbocation, not a delta positive, and we're going to form bromoethane. Okay. Now notice this is, instead of dibromo, this is just single bromo, so monobromo, mainly because the other atom in this molecule was hydrogen, and that's been added onto the end there. Okay, so there's your product. It gets a little bit tricky when you've got asymmetrical molecules. We'll kind of show that later on. Okay, so we'll show it now then. Right, so we've got reacting hydrogen halides. These are unsymmetrical alkenes. So when we react these, we produce two different products. Got to be really, really careful with this. Okay, this is a key area, and you've just got to watch out for it. Okay, so the amount of the two products is determined by the stability of the carbocation intermediate. Remember we talked about that just before. That was that middle part there. Okay, so the more alkyl groups that are bonded to the carbocation, the more stable the intermediate is. Okay, and you've got to think about the middle bit and think about, is it the middle stage of the full reaction, and think about, is it stable? Which one is more stable? Which one would form the most stable intermediate? Okay, so this is because what we've got is alkyl groups. Remember, these are things like CH3, CH2 parts to the molecule, basically just alkyl groups. It could be an ethyl methyl, doesn't really matter. But anyway, these push electrons into the positive carbocation. This makes it more stable because it stabilizes the carbocation, and it means it's more likely it will form. Okay, so you're looking for what's bonded to that carbocation. So let's have a look. This one's a primary carbocation. Okay, the R group just represents an alkyl group. Again, it could mean anything. The red arrow just shows you where the electrons have been donated to. Remember, these push electrons into the carbocation. This is what we call a primary carbocation because the carbon is attached to one alkyl group. So we call that primary. We've got secondary and then we've got tertiary. So secondary's got two alkyl groups attached to the carbocation. So this is called secondary. And tertiary has got three alkyl groups. Now, the one which is the most stable is this one because we have three alkyl groups all pushing electrons in to this area of, to this carbon which has very few electrons because it's got this positive charge. So this is going to be more stable. So in terms of the reaction mechanism, going via a tertiary carbocation, the products produced going via tertiary carbocation are going to be more likely to form than going via a primary carbocation or secondary for that matter. So really look out for what type of carbocation you produced. Obviously if you can form a tertiary or a secondary, the products via these are going to be more likely than via a primary. So we'll have a look at this specific example. So here we've got one here. This is propionine. Okay, you can see it's an unsymmetrical alkene because obviously you can see the double bonds on one side of the molecule. So this is propionine. Here's our hydrogen halide again. Okay, so we've got delta positive, delta negative. So what we're going to do is going to do the same mechanism as what we did before. Okay, so we'll double bond, goes in for the delta positive, breaks that bond. The hydrogen adds onto the molecule. There's the hydrogen there. Okay, so it wasn't there before, we've now added it. Now we've formed a carbocation. This is a primary carbocation because we've only got one ethyl group. Effectively, this whole bit is attached to the carbon. The rest of them are hydrogen. So this is primary. Not very stable. Here's the lone pair. Okay, let's have a look at the other option. Okay, so this is where the hydrogen now, instead of adding there, it adds there instead. So there's the hydrogen. Now, if you see, the positive carbocation is now in the middle of the molecule. So now we have two methyl groups either side pushing electrons in. This is more stable because this is a secondary carbocation. So basically, the hydrogen can either add there or it can add there. But the one which is going to give you the most stable intermediate is adding the hydrogen there, and then you're leaving your carbocation there. Okay, so that's what we've got. So let's have a look at the first one. Bromine obviously adds on there and we form one bromopropane. We'll call this a minor product because we don't get much of it. The intermediate isn't as stable as this version, which this one you get two bromopropane, which is a major product. So you can see here that we've got two different products, but you're going to get more of the two bromopropane because it's going via a secondary carbocation than one bromopropane, which is just a primary. Okay, so let's look at another example. So we've looked at bromine, we've looked at hydrogen bromide. Now we're going to add another molecule, and this is sulfuric acid. Okay, so alkenes, they react with cold, concentrated sulfuric acid, and they form alkyl hydrogen sulfates. Okay, so this is quite a big molecule, so you've got to be ready for this one. Right, sulfuric acid is used as a catalyst in this reaction. This actually makes an alcohol from an alkene. So when you do the alcohols topic, you'll notice that there's a specific reaction that you need to know, which is going from an alkene to an alcohol, and you use sulfuric acid. This mechanism is just showing you how the sulfuric acid acts as a catalyst. Okay, and this is quite detailed, so make sure you know this effectively the back of your hand, I suppose. So this mechanism, like I say, it shows how it interacts with the alkene to form the intermediate, and the intermediate is alkyl hydrogen sulfate. So let's have a look. So this is sulfuric acid. This is the formula for it. H2SO4. You've got to know that formula. We've just put some polar charges on here on the oxygen and the hydrogen. There's our alkene that we're going to use, and we're going to use this to make an alcohol. But we're going to use sulfuric acid as a catalyst. So the mechanism is actually pretty much the same, so it's not too bad. Okay, so there we go. There's the first step. Remember, it goes from the double bond to the delta positive, and then the electrons move into the oxygen. So effectively, this hydrogen is now going to be bonded to this molecule. Okay, so there it is. That's the hydrogen we've just added on. We have a carbocation intermediate just as normal, and then what we've got left is this sulfate, or this hydrogen sulfate group here. Hydrogen and then sulfate is SO4, SO42 minus. So we've got this negative charge because we've just nicked the hydrogen from the end of it. Lone pair on the oxygen, and this is going to go onto here. So we're going to have a bond or an arrow going from here onto there. There it is. Okay, so it goes onto there, and you form your delta positive. So you can see that our intermediate is now formed. This is called our alkyl hydrogen sulfate. So this one is ethyl hydrogen sulfate because we've got 2 carbons, and there's the hydrogen sulfate bit, which is this bit at the bottom. So we're going to see, obviously this is just our intermediate. This is not an alcohol. So we're going to see how we can take this product here, this intermediate, and take it further to form your alcohol. So let's have a look. So the alkyl hydrogen sulfate that we've just made in the previous step, this has to be reformed. The sulfuric acid, sorry, has to be reformed. So we're going to take the alkyl hydrogen sulfate and basically going to add cold water to the ethyl hydrogen sulfate that we've used before, and this will form ethanol. We call this hydrolysis. So it's really, really important. So if we have a look on here, there it is. There's our alkyl or ethyl hydrogen sulfate. We're going to add water to it. There's no mechanisms required here. We just form your ethanol. There it is there. Okay. Now, obviously, the OH has been added here. We can get an OH from here, but we also have a hydrogen that's left over from this water molecule. And all the hydrogen does is just adds itself onto the oxygen when this breaks off, and we form sulfuric acid is remade. And that's proof that this is a catalyst. We call this hydrolysis because we're basically, the word lysis means to break something or to cleave. So hydro meaning water. So all we're doing is we're breaking a bond using water. And you might see hydrolysis quite a few times. So that's all it means. So hydrolysis meaning breaking using water. Okay, so here's the overall reaction. Look, step 1, we took our alkene, reacted with sulfuric acid, and we produced our ethyl hydrogen sulfate, which was this molecule here. We then took the ethyl hydrogen sulfate we made, we added water to it, so it's got to be cold water, and we form our alcohol. This is ethanol, plus your sulfuric acid is reformed. There's your catalyst. Okay, so make sure you know how this works. Quite detailed, and it actually overlaps with the alcohols topic as well. So there it is, sulfuric acid is reformed. Also, we're using asymmetric alkenes. We can also produce 2 products as well. So just be aware of the types of products that we can produce. Just like with I showed you with the other one, you get your minor and your major. You can also get this here as well. So just be wary of how this could pan out. Obviously, this one is a symmetrical one, so we can only get 1 product, but you could get 2 with asymmetric alkenes. Okay, alkenes are really useful for plastics, making plastics or types of polymers. So alkenes are monomers. Okay, so these are just single these are just single units, and we can join these monomers together to form polymers, and it goes via an addition polymerisation process. So let's look at some examples of polymers. We have, obviously, they're made from monomer units. These are the things that make them up. We can have natural and synthetic ones. So natural polymers, things like proteins and natural rubber, and synthetics are polyethane and polypropene. So these are the things which we can make synthetically. So let's have a look. So we've got polymers. Obviously, these have been used for a while. Charles Goodyear, in particular, he discovered vulcanized rubber. And basically all he did is he added chemicals to a natural rubber, and he made it harder wearing, which was ideal for tyres. So obviously we can still see Goodyear tyres around now, but it all started from this guy called Charles Goodyear. I think he discovered it by accident as well. I think he was looking for it, but I don't think he purposefully actually designed the chemicals. I think it was an accidental discovery, but he did want to look for a stronger rubber. And obviously in the last 100 years they've been developed. We've got plastics such as water bottles like polyethane, nylon, Teflon. Obviously this is the non-stick stuff you get. And these polymers obviously revolutionise the way we live, and we use plastics all the time. The likelihood is you're probably sitting within a few meters of plastics. You may even be wearing polymers, like synthetic polymers. Obviously, we've got new polymers are being made all the time. Obviously, we've got things like electronic gadgetry, touch screen, etc. So these things are becoming increasingly more used, but obviously we need to look at ways in which they'll be sustainable so we can recycle them, etc. So let's have a look. So to make your polypropene, okay, which is the type of plastic we've seen before, we need a monomer propene, and we need to add a few of these together and we make polypropene. Okay, so there's propene. Okay, I've drawn it just so we can see, just so we pronounce the C double bond O. Basically what happens when we join these together, the double bond opens up and we form our polymer. Now there's a few things to kind of notice here as well. The N bit means that we've got a lot of repeat units, so that's quite important because this is our repeat unit, this bit here. This is your alkene obviously being expanded. So the double bond's obviously not here anymore because it's broken. And we now have these trailing bonds, and these extend beyond the brackets. So make sure when you're drawing your brackets that you draw your trailing bonds that extend beyond this. Okay, so this double bond's obviously opening up. And this one's showing 2 repeat units. Now you can see here, these are 2 monomer units, 2 monomers here, and this is 2 repeat units. Notice we don't have the N here now, because in the exam what they might ask you to do is just show you a specific number of repeat units. This one's showing 2, putting an N there suggests that you have loads of them, and that's not what they're after. So they're after 2 repeat units in this case. So yeah, polyalkenes, these ones here, these are now saturated molecules, normally non-polar, because they're just full of carbons and hydrogens, so they're pretty stable, they're unreactive. Obviously this is a downside because this can now make it really difficult for them to degrade in landfill because they are so stable, so they're kind of like a victim of their own success, I suppose. So it's important to be able to kind of recycle these, or maybe reuse them or do something with them instead of putting them into landfill, because obviously that's not brilliant. It's not the ideal solution. Okay, so let's have a look at some of these properties. So we've got intermolecular forces, and these govern the properties of polymers, a bit like with simple molecular as well. So most polyalkene chains are non-polar. Okay, so all they have is just van der Waals forces between the chains. Remember, your van der Waals forces are the weakest forces, weakest intermolecular force. Okay, so basically, the longer the chain, the closer they are. The closer they can kind of pack together. And the more kind of surface area you've got for the van der Waals forces to take a hold. So basically, the longer the chain, the higher the melting point. These chains, which are shorter and have a lot of branching, remember branching means they can't pack together as closely, they tend to be more flexible and they're weaker. Okay, so they're not as strong as your longer chains, which are more straight. Okay, so yeah, polymers with no or very little branching tend to be, and long tend to be more rigid and stronger. As long as you can identify the properties of these and what it means in terms of the molecule, then that's the main thing. So you've got some polyalkenes have halogens in, so PVC, which you might use in drain pipes, etc. These obviously have more stronger permanent dipole-dipoles because you've got a polar part to it. You've got the chlorine bit now, which is creating a polar bond, and we can get forces stronger than van der Waals when we've got a dipole-dipole. So obviously these are going to make the plastic a little bit different, and things like PVC is pretty useful in terms of outdoor wear. So things like obviously like your drain pipes and guttering, etc. And it can weather storms. You know, it's really strong. It's durable even when it's covered in water and wind and snow and frost and things. It still generally lasts a reasonable length of time compared to other properties. It's quite lightweight and it's cheap as well, so it's useful, things like guttering. Plasticizers, right, these are extra things which you can add to your plastics, and you can change the properties of them. Okay, and plasticizers are a good way of doing this. So what they do, plasticizers make the polymers more flexible. Okay, that's quite useful if you want to make things like fabrics for clothing, or materials for things like bouncy castles, etc. You want it to be more plastic. So plasticizers slide between the polymer chains, and what they do is they push them apart, so it makes them a little bit softer, weakens the intermolecular forces between the chains, and they can now slide over each other, and you can bend the plastic a lot easier, which is can have useful properties for certain things. So plasticizers, normally, like I say, PVC, you can add plasticizers to PVC and it can change the properties. So let's have a look. There's your chloroethane. There's your chloroethane. And then we've got loads of these, N, so we've got a number of them. We join them together and we form polychloroethene. Okay, so notice we still keep the ene bit. Okay, poly just meaning more than one. So we're joining them up, and there is an example of polychloroethene. Okay, now PVC is made from long, closely packed polymer chains like this. They're hard but brittle, and like I say, they're used in drain pipes, so that's pretty useful. But it's used if you have a plasticizer, same polymer, exactly the same polymer. We haven't changed the polymer. All we've done is added a plasticizer, pushes the chains further apart, makes it more flexible, and this is ideal for things like I said, clothing or electrical wiring. So you can see this is softer, same plastic. You wouldn't believe it, but it is. It's the same plastic. All we've done is added an additive to it, and you can see they're clearly different properties to them. So that's really useful for a chemist to be able to do that. And that's it. That's the alkenes topic for AQA, basically, in a nutshell. I hope that was pretty useful. There's two bits really to this. Is your mechanisms are the most important things really. They generate loads and loads of marks from this, and obviously the polymers bit as well, because that's a use for alkenes, is to make plastics, and that's the whole point of it. So yeah, like I say, just finally, you can, if you want to purchase these PowerPoints, so you can use them for revision or supplementary revision, you obviously can. If you click on the link in the description box, you'll be able to find them there. But that's it. Bye bye.